So I thought we would we'll use a step size of 0.005 and then compute by hand. No, I'm just kidding. We're not going to do that. We really aren't.
This is ridiculous.
Right, so we're not going to do it. The ridiculous thing with step size like this. But I did it with my software and got an answer of 4.7115. Remember, the answer should be 2 plus e, so 4.71828. It's off a little bit. It's getting better. And yeah, I mean, if I said step size 0.001, then that would have helped a lot. So one possible source of error is round-off error, but we'll focus on the error that comes from a straight line being used to approximate a function that may be curved, and that's going to happen. But that's called the local truncation error if it's at the end of one step, and it's called the global truncation error if it's at the end of a multiple step process. So that's the global function error is the error in approximating the function value at the desired endpoint and the result of the truncation error at every step. So in other words, get a little truncation at each step. That's called the local truncation error, and then we get a global truncation error to see how far are we off from the real thing after we've had all these local truncation errors. And so the absolute error, the relative error, the percentage error, they're pretty straightforward, and what they are, the true value minus the approximated value in absolute value is called the absolute error. The expression true value minus approximated value over true value is the relative error. In other words, dividing by how much the item itself is, right, the true value, will give us the relative error. What's the relative error? And then if we multiply that by 100 and stick a percent sign on there, which means multiply it by 100 and then divide by 100, it's called the percentage error, but really it's the same thing as relative error.
That's the loveliest thing I've ever heard.
Well, I'm glad.